Hey, where would you rather be right now than watching an Algebra 2 group test video key? Nowhere is the correct answer, so let's get this going. On number 1, we have a piecewise function, and there's 2 different pieces, and you just have to choose the right piece based on what x value you're plugging in for A, B, and C. So remember, f of -1 means this is your x value, this is your x value, this is your x value. And so use the top piece if your x value is less than or equal to 0, and use the bottom piece, which we'll highlight in orange here, if your x value that you're plugging in is greater than 0. And so if we go down to part A, we can see that we're plugging in -1. Since -1 is our x value, which is less than or equal to 0, we're going to plug -1 into this piece and get -3 times -1 plus 4, which is equal to 7. Okay, going down to part B, now we're plugging in 2 for x, which that x value of 2 is bigger than 0, so we get to use the orange piece this time. And that is plug in 2 for x, so you get 2 times 2 plus 11, which is 15. Okay, coming over to C, x is 0, so we're going to use exactly 0 for this piece because it's or equal to 0. So again, we're plugging into the blue piece to get -3 times 0 plus 4, which is equal to 4. Now part D is a little different. We're going to find x when f of x is equal to -5. So we have to try both pieces and see what happens. So first we're going to plug in, or use the blue piece. So we're going to set the function, that piece of the function, equal to 5. So looking at the blue highlighted piece. Solve this for x, so subtract 4. And you get -3x equals 1. And divide by 3 to get x equals -1/3. Now, what you have to check on this problem is, since we used the blue piece, this is the x value we got, are we even allowed to use x values of this value on the blue piece? So that's where you look over here and make sure your answer fits this part of the definition. Since our answer is -1/3, which is less than 0, that means we were allowed to use the blue piece. So remember, on a graph, like maybe let's pretend this is the graph. If the blue piece was only graphed right here, for example, then this x value wouldn't exist on that piece. And so you wouldn't be able to use it. But you can check, you don't need a graph to check it. You check it just by seeing if it fits the definition up here. Now the orange one's going to end up not working, so you can see what happens when it doesn't work. So if we're going to set the orange piece equal to 5 also. Subtract 11, divide by 2, and you get x equals -3. But in the orange piece, so this is a point on the orange piece, -3, 5. If this line went on forever in both directions, it would work. But we're only graphing this line starting with x values that are greater than 0. Our x value is not greater than 0, so we can't include this answer. So can't use this answer. So that's, you don't need to write that, but whoops, wanted to use this pencil. But it is something that doesn't actually fit in our mold, so it's not a solution. All right, number 2, we're just using a graph to answer the same questions. Same types of questions as up here. F of -2 is when x is -2, so come over to x is -2 right here, find the y value, and you get 4. F of 0 is the y value when x is 0, and you get 0. And f of 1, so this is where there's like a hole right here, and there's a not hole right there. Use the value at the one that's filled in, so f of 1 is 1. And then this question says find the value of x when f of x equals 1. So this is your y value. So a y value of 1, if you want to, you can draw a horizontal line through y equals 1, and everywhere that it hits, but it hits here at 1 and at -1. So here we're finding our x values. So x equals either -1 or 1. All right, now we graph this. This one, normally you'd see a plus a number here. So if you don't see anything, it's just +0. That means our y-intercept is 0 and our slope is 2. So color code these here. We're going to graph this line, but only for certain x values. I'm going to graph the whole line for the blue one. And then I'll do the orange one differently, so you can two different ways to kind of think about it. So we have a y-intercept of 0 and a slope of 2. So up 2 over 1, up 2 over 1, up 2 over 1, and we can go down 2, left 1 in the other direction, like that. So the entire blue line, just y equals 2x, would look like this. But we're not graphing the whole line. We're only graphing this line for x values that are less than 3. So I did make sure as I was doing this that I went out to an x value of 3 right here. But the blue line is only graphed for x values less than 3. So starting at this point and going this way. And since it's less than 3, that's where we get a hole in the graph right there. And so I had to get rid of all this. And then this point actually is a hole instead of a filled-in circle. And so that's how you can kind of draw the whole line and then erase part of it. Now, if you want to do it a different way, for the orange line, we have a slope of -1 and a y-intercept of 1. So you can start at a y-intercept of 1 and then just use your slope until you get to this x value, and then that's your starting point. So we start here and we go down 1 over 1, down 1 over 1, down 1 over 1. So now we're at this point right here. So at 3, -2 is where this graph starts. And that's going to be a solid point. And then keep using your slope, down 1, right 1, down 1, right 1. And then you connect those points. So you can either graph the whole line and erase, or figure out, use your slope and y-intercept to get to this x value, and that's where each line kind of like starts or ends, if you want to think of it like that. All right, now we're solving some equations. So some of these get a little funky, but they're still pretty straightforward as far as solving equations. On this one, we subtract 3 to get -2x equals -14. Divide by 2, and x equals 7. On this one, we have x on two different sides, so subtract 2x first. And then I'm also going to add 10 at the same time. And you just get 3x equals 45. And so divide both sides by 3, and x equals 15. There's different ways you could do this. I like to keep my x's positive when possible in equations. You don't have to do that in solving equations, but I do recommend that when you solve inequalities, make your x's positive. It helps avoid a potential mistake. So I moved this over by subtracting, moved this over by adding, and that's where that came from. On number 6, a couple things you could do first here. You could get rid of this 4, or you can distribute the 5. I'm going to distribute first and get 5x plus 5 minus 4 equals -24. And then you can combine like terms here. 5x plus 1 equals -24. And subtract 1, so 5x equals -25. And finally divide by 5, and you get x equals -5. Okay. On number 7, same thing to distribute. So I'm going to distribute the 5. I'm going to distribute this negative, which is the same as multiplying by -1, which will just change the signs of all those numbers essentially. So distribute first. Over here we get 10x. 10 doesn't look very nice. 10x plus 20 equals, distribute your negative, so it becomes positive x plus 8 and then plus 7. And then combine like terms when possible, which we can on the right side here. And now I'm going to subtract x and subtract 20, which will get me -5. And so divide by 9, you get x equals -5/9. can just leave it as a fraction, or you can use a calculator and divide it if you want. All right, on this one, probably the easiest way, as we had discussed in class at some point, is to get rid of this fraction. So if I multiply both sides by 4 first, let me white out this number 8 so it doesn't look like part of the problem. Multiply by 4 first on both sides, so times 4. Notice how I use parentheses over here because I have to distribute. These cancel each other out, leaving you with just x plus 5 on this side, which is what we wanted. And then distribute the 4 and you get 12x minus 28. Okay, and now I'm actually going to subtract 12x and get negative 11x. Subtract 5 and get negative 33. Divide both sides by negative 11, and so you get x equals 3. And that's how you can do that one. All right, now in these problems, I just said pick one to show all the solutions on a number line and an interval notation, rather than do it on every single problem. On the individual test, I'll give you a specific one that you had to do, but you will have to do interval notation and graph your solutions on a number line. So on number 9, the first thing I want to do is make my x positive. So I'm going to add that to the other side. So I get negative 5 is less than 3x plus 10. And then subtract 10, so you get negative 15 is less than 3x. And finally divide by 3, so you get negative 5 is less than x. But remember, read it this way, it's x is greater than negative 5. And so if x is greater than negative 5, I'm going to put all these on a number line and interval notation for you. So if x is greater than negative 5, we have negative 5, negative 4, negative 6 here. Start at negative 5 and go numbers that are bigger than negative 5, which is that way. In interval notation, that is starting at negative 5, not equal to negative 5, and go on forever to the right, so negative 5 to infinity. On number 10, you could distribute first here, or you could divide both sides by 2. I'm going to divide by 2 first, and that just cancels out the 2 on the left side, giving us 4x plus 12 is less than 8. And then subtract 12, so you get 4x is less than negative 4. And divide by 4, so you get x is less than negative 1. Putting that on a number line, we have negative 1, negative 2, and 0 over here. And less than negative 1 goes this way forever. And that is negative infinity up to negative 1, because these numbers going forever this way, so you're going to negative infinity over here, and then you have to stop at negative 1. All right, now on an OR problem, just solve these two things separately. So first I have a negative x, so I'm going to make that positive. Move it to the other side, so you have 6x minus 20. Then add 20, so you get 30 is greater than 6x. And divide by 5, or 6, sorry, so you get 5 is greater than x. But remember, read the x first, so x is less than 5. And you can even write it that way if you want. Looking at the other one, subtract 32, our x is already positive, so let's keep that there. So x is greater than 30. Divide by 5, and you get x is greater than 6. So on a number line now, we have 5 here and 6 here. X is less than 5, goes this way. And x is greater than 6, goes the other way, because you can't be both less than 5 and greater than 6 at the same time. And so our solutions really should say x is less than 5 or x is greater than 6. And then in interval notation, less than negative 5 is negative infinity to 5. Sorry, I may have said less than negative 5. Less than 5 is negative infinity to 5. And then greater than 6 is 6 to infinity. And then this is where you put a union symbol in between. Okay, now in this one, a compound inequality. what you can do on this one, I'm going to show you a little trick on this, but you could treat this as two separate problems like this. So ignore that, solve this problem like we normally would, and then ignore the other one, get rid of that, and then just solve this problem like you normally would. So you would want to get the 10x over here. That's probably the best way to do it. But I'm going to show you a little bit of a trick here. So you can subtract 12 from all three sides. Subtract 12, subtract 12, subtract 12. And that gives you negative 30 is less than or equal to negative 10x is less than 36. And now you can divide by negative 10, but when you do, since you're dividing by a negative, this is the kind of thing that we avoided talking about for the most part because this is where mistakes tend to happen. If you divide by a negative, normally what I would have you do is add 10x to like this side, and so the x would end up on the other side of this inequality symbol. But the shortcut is you can just switch it when it was negative to begin with. And so this ends up like this instead. Now this is written in a weird direction. Normally we read it with a smaller number first, so it's negative 3.6 is less than x, which has to be less than 3, less than or equal to 3. And so this is where on a number line, x is between two numbers, and so the arrows go towards each other. So we're just going to start with negative 3.6 here, and 3 here, and it has to be greater than 3.6, but less than 3. So that's when it goes like that. And then in interval notation, start with the smallest number, negative 3.6, and go to the biggest number, 3, and it's allowed to equal 3. All right, now we got some absolute value stuff here. So get the absolute value by itself first, which this one already is, but notice over here it's not. So I'll show you how to handle that. But remember, this is distance from 0. So our distance from 0 can either be 19 or negative 19. So this is what it's talking about when it says set up two cases. You have where the distance is 19 or the distance is negative 19. And then you just solve these separately. So add 5 and you get x equals 24. And add 5 again and you get x equals negative 14. The steps will always be the same, which is nice. So those are your two solutions there. We should actually check for extraneous solutions, but I didn't put any extraneous solutions on this. On 14, so this is where you want to get the absolute value by itself. Sorry about those reminders popping up there. Get the absolute value by itself by subtracting 5 first, because the negative 2 is multiplying, so you can't combine the 5. You can't do 5 minus 2. It's order of operations. You got negative 2 multiplying this stuff, but also don't distribute. But it is showing multiplication. So subtract 5 and you get negative 14. Then just divide everything. Oh my gosh, sorry. Then just divide everything by negative 2. And so you get x plus 3. Absolute value of x plus 3 is equal to 7. Now it looks just like number 13. And so now we can do our two cases where our distance is equal to 7 and where our distance is equal to negative 7, our distance from 0 on a number line. Solve them both and subtract 3, so you get x equals 4. And subtract 3 again, and you get x equals negative 10. And so there you go there. All right. Now, absolute value inequalities. So this is where our distance has to be less than or equal to 22. So on a number line, that's 22 to the right. And then, so if 22 is over here, less than 22's got to go that way. Just ignore that circle. And then, but you could also be negative 22. So 22 to the left, and then numbers can go that way. So this is where you have to say, all right, our distance can be less than or equal to 22, and to the right, it can be 22 to the right is what 22 means, or it can be greater than or equal to 22 to the left, and negative 22 just means to the left. And so then you solve these by subtracting 7. So x is less than or equal to 15. And at the same time, x has to be greater than or equal to negative 29 after you subtract 7. And you can put these on a number line and an inequality notation, or on a number line and an interval notation as well. But since we already did that up here, I'm not going to talk about that again right here. Let's go to 16. 16, same thing. Now we need our distance to be less than 20. And so negative 4x minus 20 has to be less than 20 to the right on a number line, or greater than 20 to the left. So greater than negative 20, that just means to the left. Remember, that means to the left. And then we solve this, or add 20. So negative 4x is less than 40. And then we're going to add 20 over here. Negative 4x is greater than 0. Now we have a negative 4x, so move it to the other side. So now we have, if you add 4x, you get 0 is less than 4x plus 40. And over here, you get 0 is greater than 4x. Back to the orange one, subtract 40, so you get negative 40 is less than 4x. Divide by 4, and you get negative 10 is less than x, or x is greater than negative 10. On the green one, you can just divide by 4, and you get 0 is greater than x, or x is less than 0. So x is less than 0, and x is greater than negative 10 at the same time. That's an and problem because they can both happen at the same time. And finally, number 17. So we want to make 17 look like 15 and 16, so we want to get the absolute value by itself. What's weird about this one is since there's a negative here, I'm going to take this entire thing and move it to the other side, all this. So my first step, I'm going to add that whole thing I just highlighted in blue. And what that's going to give me is 8 is greater than positive 3 times the absolute value of 2x minus 5, and then minus 16. And so you can move this entire thing to the other side. Now from here, we can solve it like normal. Add 16, so you get 24, is greater than 3 times the absolute value of 2x minus 5. I'm going to write this in the other order just because that's how we're used to seeing it. So I'm just going to write this first and then put less than 24. So we have 3 times the absolute value of 2x minus 5 is less than 24. We do have to get rid of this 3. So divide by 3. And now this looks like the other problems we've done. So our distance has to be less than 8. So 2x minus 5 is less than 8 to the right is what that means. Or it has to be greater than 8 to the left on a number line. And so add 5, and you get 2x is less than 13. Divide by 2, x is less than 13 halves. And the blue one, again, add 5. So you get negative 3, and divide by 2, and x has to be greater than negative 3 halves. And there you go. There's all your solutions.